Okay, we're continuing with Chapter 9 in the statistics textbook. In this video, we're going to go through the second section, which is on changing standard deviations in regards to how a change in standard deviation affects the correlation coefficient. Okay, so it says, the appearance of a scatter diagram depends on the standard deviations. For instance, look at Figure 3. So let me bring in Figure 3 here. It's on the next page. Okay, so here's Figure 3. It says in both diagrams, R is 0.7, positive 0.7. However, the top one looks more tightly clustered around the SD line. So if we take a look here, yeah, this data at the top is more clustered around the SD line than this data at the bottom. These data points at the bottom. But the correlation coefficient is the same. Now, if you're like me, when I first learned this was actually really confusing because this seems to contradict the way we've been analyzing scatter plots in relation to correlation coefficient up to this point. The correlation coefficient is a measure of the degree to which data points cluster around a line, some line, and we've consistently gone through different problems where we're looking at, okay, we have these data points here, right? They're more tightly packed than these. So this is a higher correlation coefficient. This is what we've done time and time again for many problems. So how could these possibly have the same correlation coefficient? There seems to be a contradiction here. Okay, well, what's going on is that up to this point, all of the examples we've looked at, the problems we've worked, where we're comparing different scatter plots and analyzing the difference between the correlation coefficients, in all previous cases, the overall spreads of the different data sets have been the same. If you go back through Chapter 8, in the beginning of this chapter, you'll see that's always the case, as opposed to here. What's going on here is that look at the spread of this data in the Y direction and the X direction, and compare that to the spread here in the Y direction and the X direction. These spreads are different. In general, this is a larger overall spread. Now, the reason why I'm saying that in general it's a larger overall spread is because, well, you have a spread in the X and a spread in the Y, right? But then more than that, in the X and Y, all of the points kind of spread out, meaning that so we could have this data here could be spread out more in the X and the Y. So like think about the range both the range in the X and the range in the Y could increase, but you could still have the points be like this and it still spreads out, right? So what I'm saying that in general, this data is more spread. The X range and the Y range increases, but then the points in overall spread out as well. Okay, now, but because the correlation coefficient is based on the z-scores of the data points, or the standard units, we know that standard units are relative, specifically relative to the standard deviation. So it's not about, so the correlation coefficient is not about strictly how spread out you are, but how spread out you are relative to kind of the characteristic spread of the data, the standard deviation of the data. And so what this means is that if you have a larger range, like in the X and the Y, here the range is bigger than here. Well, because the correlation coefficient is based on z-scores, which is relative to standard deviation, then because this is going to have a bigger standard deviation than this, then you have more freedom for the data points to spread out a little bit from the standard deviation because again, it's a relative, right? Percentages, if the standard deviation is 6, 1/3 of 6 is 3, If the standard deviation is 21, 1/3 of 21 is 7, you have freedom to spread out more, right? 7 is greater than 3. And so that's why you can have these two data sets having the same correlation coefficient, even though these are more spread out around this line here, these data points. Now, if the overall ranges were the same, then no, this wouldn't make any sense. Based on the definition of the correlation coefficient, it wouldn't make any sense to have more spread out points around like the same line and have the same correlation coefficient. No, that would make sense. Now, but what you can also see here is that this sheds some light on this question that we answered in the exercises from the previous section. This question about two weathermen computing the correlation between daily maximum temperatures for Washington and Boston. One does it for June, the other does it for the whole year. And we were wondering why it was the case that, so if you just do this in June, you get some data points out here, right? This was, let's see, Washington, Boston. But if you do it for the whole year, you get more data points down here in the colder months. Why did we say that in general this would increase the correlation coefficient? In general, because, you know, you could have some weird things happen, maybe assuming the months are behave normally, the temperatures. Well, we can see why this is the case, because we've increased the range from just June. Here's the range for the whole year. Here's the range, right? But we didn't, when increasing the range, we didn't spread out the data, right? We didn't all of a sudden spread this out more in the increased range. No, it had like the same spread, just a larger range. Well, in that case, that's going to increase the correlation coefficient, right? In the same way that if we started here and we increased this range, but made this more tightly packed, the same level of compactness as this, well, that's going to be a higher correlation coefficient. Okay, now, but just to show you, if we look back at some of the previous examples we've worked on from previous sections in the previous chapter, you see the spreads are all the same here. We're comparing correlation coefficients with the spreads all being the same. And in general, this was the case for all of the different examples we looked at previously. Okay, but now from a quantitative standpoint, why is this the case? Like, what would we have to do to these data points numerically to create these data points here and not change the correlation coefficient? What's exactly happening here? Well, we can understand quantitatively what's going on if we think about changes of scale. And if we took any set of data and we wanted to do a change of scale to the X or the Y, any one of the two variables, in any kind of change of scale, any number of changes of scale, what you can think about is that we can change the average without changing the standard deviation. We can do that. But with a change of scale, there's no way for us to change the standard deviation without changing the average. We can't just change the standard deviation alone with a change of scale. Because what happens is, if the only way we can change the standard deviation with a change of scale is by multiplying all the data points by the same number, and that multiplies the standard deviation by that number, and it also multiplies the average by that same number. And so the result of that is you've got something like an average changing from 6 to 18, and a standard deviation changing from 1 to 3. And so in this case, you're allowed to have data points farther away from the average in terms of magnitude, because look, 3 is bigger than 1. You can go a little bit farther from 18 than you could from 6. You can spread out a little bit more without changing the z-score. And so with this in mind, if you're ever comparing scatter plot data in terms of the correlation, one thing you want to note is, are they spread differently? You have to keep in mind, yes, how well are they clustered around some line, but also you have to look at their differences in spread. But you don't have to worry about if the point of averages are different. here the point of averages are the same, but what if the point of averages here was located at, same shape of data spread, but this is located at x is equal to 500, y is equal to 400, and this is just at x is equal to 4, y is equal to 2. Well, it seems like that could change the z-scores, right? No. That would be a change of scale related to just strictly a change of average. To move this point of averages to the point 400, 500, you just need to add some value to all the x values and then another value to all the y values. We know that doesn't change the correlation coefficient. However, if you multiply all of the values of one or both of the variables by a certain number, that is going to change the average and the standard deviation at the same time, allowing for more spread, to spread out in general, not spread out just purely from a range standpoint, because if in that case, this could be more spread out, but the correlation coefficient increases. So just in general, the cloud spreads out. You can spread out more and not change the correlation coefficient. Okay, so if we finish reading through all of this, R is 0.7 in both diagrams. However, the top one looks more tightly clustered around the SD line. That is because its standard deviations are smaller. The formula for R involves converting the variables to standard units. Deviations from average are divided by the standard deviation. So R measures clustering not in absolute terms, but in relative terms relative to the standard deviations. To interpret a correlation coefficient graphically, draw the scatter diagram in your mind's eye so the vertical standard deviation covers the same distance on the page as the vertical standard deviations in figure 6 on page 127. Yeah, I'm not sure what they were talking about here. And likewise for the horizontal standard deviation, if R for your scatter diagram is 0.4, it will probably show about the same amount of clustering around the diagonal as the one with an R of 0.4 in the same figure at the top right. If R is, yeah, so this was, I'm not sure what they were going for here, but I think we covered it pretty clearly on how to compare the spreads of two separate scatter plots. Okay, I'll say it again. It doesn't matter where the point of averages between two scatter plots is. If one set of data is more spread out from the perspective of like an even increase in spread in the up, down, left, right directions, but it has a larger overall range, then that additional range can still even out the correlation coefficients between the two data sets. Because the larger your range, the more freedom you have to spread out in relation to the correlation coefficient. As opposed to here, well, this is more spread out than this and this and this, but the range isn't changing. The overall ranges of all of these are the same. If you increased the range of these data points here, then even though these data points are more spread out around this line than these data points, these have a more tight cluster than these, because of that additional range, these two correlation coefficients could be evened out. Both could be 0.95. But without the increased range, then no, you're looking at, okay, how tightly clustered are they around a certain line? Well, this is more tightly clustered than this, so higher correlation coefficient. Okay, so here's figure 3, and that's it for this section. Okay, now let's take a look at these exercises. It says in the figure below, 6 scatter diagrams are plotted on the same pair of axes. In the first, the points are marked A, in the second B, and so forth. For each of the 6 diagrams taken on its own, the correlation is around 0.6. Now take all the points together for the combined diagram. Is the correlation around 0, 0.6, or 0.9? So, okay, you've got, what they're saying is it's like you could have one scatter plot with all the A's, another separate scatter plot with all the B's, another separate scatter plot with all the C's, but then you could bring them all together. Each of those scatter plots separately has correlation around 0.6. Now, if you bring them all together, what's the correlation going to be? Well, okay, we can see that as a group, we're going to get a bigger range than we would for each of these separately. right? Like, look, we've only got A's out here. We've only got 2 F's out here. We've only got 2 E's out here. The D's are really don't spread out much in terms of, at least in terms of range. So, but like, however, though, it's not like any of these data sets on their own are more spread out in general. Each of these data sets on their own looks like it's going to be something like this. But then when we combine them, we get something like this. So we get a bigger range, but from like a general cloud perspective, the data doesn't spread out anymore. It's still that same degree of clustering, but a bigger range. So we know that's going to increase the correlation coefficient. So point 9. The National Health and Nutrition Examination Survey on page 58 also covers children. In Haynes 2, at each age from 6 to 11, the correlation between height and weight was just about 0.67. For all the children together, would the correlation between height and weight be just about 0.67, somewhat more than 0.67, or somewhat less? Well, this is similar to the previous example. We would just expect the full graph for all ages to just extend this graph. Because it's not like you're going to get some drastic change between a height and weight relation for just general children. I mean, I guess if we were talking from maybe babies to toddlers, I guess so, but that's not what they're talking about here. They're talking about just general children right past toddler age, maybe 3 and up. Well, yeah, again, it's just going to be an extension of the graph. So you're going to get a bigger range graph with the same amount of spread around any given line. So we expect it to be somewhat more. Below are 3 scatter diagrams. Do they have the same correlation? Try to answer without calculating. Okay. So we've got let's see. It's like the exact same amount of spread in all of these. Exact same shape, exact same spread. The only difference is the point of averages is different between them. Well, that doesn't matter, right? It seems like it might. Look, here, this is 30, this is 550, same spread, but you have a different point of averages, so maybe like, the percent differences would change things. No. A pure point of average change of the same shape of data does not change the correlation. So no, the correlation does not change here. So, yes, they do have the same correlation, yes. Someone hands you the scatter diagram shown below, but has forgotten to label the axes. Can you still calculate R? If so, what is it, or do you need the labels? Yes, you can still calculate R. And the reason why you can still calculate R is based on the exact reason why the correlation didn't change here. It doesn't matter what these tick marks correspond to. It's all relative. It's all relative. I could put this as 1,000 and this as 500. Well, then in that case, I need to make this 0 and I need to make this 1,500. And then here, I could put whatever I want here. I could make this 50 and this 100. Then that means I need to make this 150 and this 200. Okay, now if so, what is it? Well, you just, okay, this data point is 100, 500. This data point is 150, 500. This data point is 150, 1,000. This data point is 200, 1,000. So there's your table of data points. Write them all out and go through the whole process. Okay, now let's look at these technical notes that they give to close this section. So it says if R is close to 1, then a typical point is only a small fraction of a vertical standard deviation above or below the SD line. If R is close to 0, then a typical point is above or below the line by an amount roughly comparable in size to the vertical standard deviation. Yeah, so why is that? This is based on what we looked at in the Excel sheet. Because when you have a good correlation, or the magnitude is high, the points if you look at any point, the corresponding x and y values, they're going to have close to the same standard deviation in the right direction. So if this is the point of averages, then you have this could be 2 standard deviations. This could be the SD line corresponds to having the same number of standard deviations in the x and y. It doesn't mean the SD line doesn't mean 1 standard deviation away from the average. It's the same number. It crosses through the standard deviation of x and y. Now, but you can see if we have the same number of standard deviations in the wrong direction, right? One point is this many standard deviations. Another point is this many standard deviations. Well, that's not good. And then another point is over here. That's not going to be good for the correlation. Okay, here's the second technical note. It says the connection between the correlation coefficient and the typical distance above or below the SD line can be expressed mathematically as follows. The RMS vertical distance to the SD line equals, so 1 minus the absolute value of R, that times 2, take the square root, times the vertical standard deviation. Take, for example, a correlation of 0.95. Then here's the correlation coefficient. So this is, they're calculating this here. And so now it says the spread around the SD line is about 30% of the vertical standard deviation. That is why a scatter diagram with R is equal to 0.95 shows a fair amount of spread around the line. Right, so it's 30%, the RMS is 30% of the vertical standard deviation. So if you have a larger vertical standard deviation, you're allowed to have more spread. For 0.95, it's going to be about 30% of the vertical standard deviation. If you've got a really large range in the Y, so here's a kind of a big range in the Y and a correlation of 0.95, well, then you need to spread out about 30%. It's going to be spread around 30% around that line.